Mount Etna eruption shocks. Geologists. What came out has never been seen before. Bright, glowing rock poured from the crater, defying centuries of geological records. Not basalt, not andesite. Its composition is so strange that 3 top European labs have failed to identify it. At the same time, Etna's slopes unleashed a pyroclastic flow, and seismic readings hint its deep structure is shifting, echoing conditions before the catastrophic collapse that triggered a prehistoric tsunami. If this isn't a warning, what is Etna trying to tell us? And what happens next? Mount Etna's restlessness is legendary, even among volcanoes. For more than 3,500 years, this mountain has rarely slept. Historic records and ancient chronicles agree. Eruptions are not the exception, they are the rule. On average, Etna erupts in some form more than 8 out of every 10 years. That's a higher frequency than almost any other major volcano on the planet. In the past century alone, over 60 eruptive episodes have been logged, some lasting mere hours, others stretching for months. The 2001 and 2002 events, for example, sent lava and ash across the Sicilian countryside, forcing evacuations and grounding flights. But even those dramatic moments are just the latest in a long chain. Archaeologists have traced layers of ash and lava back through Roman times, and even further, to Bronze Age settlements buried beneath black rock. Each layer is a timestamp, marking yet another burst of energy from deep inside the earth. Paroxysms, those violent, short-lived eruptions, have become almost routine here, with more than 50 recorded since the early 20th century. Etna's activity isn't just a spectacle, it's a relentless process that shapes the land, feeds the soil, and disrupts the lives of everyone living in its shadow. The volcano's constant output means that new craters, cones, and lava fields appear with startling regularity. In some years, the summit changes shape multiple times. Vents open, close, and shift position, as if the mountain itself is breathing. This long, unbroken record of eruptions sets Etna apart. It's not just a volcano that erupts. It's a volcano that almost never stops. That unyielding activity is the surface signature of something far more complex happening beneath the ground, a hidden blueprint of chambers, conduits, and shifting faults that scientists are only beginning to map. Deep beneath Mount Etna, the story of every eruption begins in a hidden world of molten rock and shifting pressure. Scientists like Boris Behnke have spent decades piecing together a map of Etna's interior, using seismic waves and chemical signatures as their guide. At the base of this system lies a vast reservoir, nearly 11 kilometers below the surface, a depth where temperatures and pressures are high enough to keep rock in a perpetual state of melt. This isn't a simple single chamber. Instead, Etna's plumbing stretches upward in tiers, with magma pausing at several levels before making its final push to the summit. Each reservoir acts like a staging area, where new magma mixes with older batches and picks up clues about its journey. The lava that typically reaches the surface carries a familiar fingerprint. Petrologists describe a mineral trio, olivine, clinopyroxene, and plagioclase, as the backbone of Etna's rocks. These minerals crystallize out as magma cools and rises, locking in information about temperature, pressure, and even the source of the melt. Most eruptions produce basaltic lava, rich in iron and magnesium, with a composition that matches what's expected from a mantle-derived source, modified by its passage through the crust. Over the last 50 years, careful analysis has shown a steady trend, a gradual enrichment in potassium and strontium, likely from the assimilation of sedimentary rocks as magma rises through the upper 10 to 15 kilometers of crust. But even with these shifts, the basic signature remains consistent. Etna's lavas are well documented, their mineralogy charted in detail across thousands of samples and decades of research. This baseline matters. It gives scientists a benchmark for comparison, a way to spot anything out of the ordinary. When a sample arrives in the lab, its chemistry and mineral content are measured against this deep, well-understood record. Any deviation, whether in the ratios of trace elements or the presence of unfamiliar crystals, stands out immediately. That's why the events of the recent eruption have drawn such intense scrutiny. The usual blueprint is so well established that even a small anomaly can trigger alarm. As field teams prepare to analyze the latest samples, they do so with the weight of decades of knowledge and the unsettling possibility that something fundamental has changed deep inside Etna. No published results. That's the first thing the lab lead noticed when searching for answers about Etna's latest eruption. Over decades, every major event at this volcano has left a paper trail. Petrological data, mineral analyses, geochemical fingerprints, all cataloged in peer-reviewed journals and open-access databases. Not this time. The usual channels, EarthChem, INGV bulletins, European Geosciences Union abstracts, are silent on the composition of the 2025 samples. Even the rapid response updates that normally appear within weeks after an eruption are missing. For a volcano as heavily studied as Etna, the absence of data is more than an oversight. It's a warning sign. Inside the lab, the lead scientist, known for her methodical approach and relentless attention to detail, has spent weeks combing through internal reports and email threads. She's checked and rechecked the submission logs from the 3 European laboratories that received the glowing material. Each lab confirmed receipt of the samples, but none have released even a preliminary data set. No major or trace element measurements, no thin section photomicrographs, no isotope ratios, nothing to compare with the tens of thousands of prior Etna samples. The chain of custody is intact, but the analytical chain stops cold. The silence is unsettling. In the past, even the most routine basalt or rare xenolith has been logged and described, sometimes before the lava has cooled. This time, the only information circulating among researchers is rumor, hints of unexpected results, whispers that the material doesn't fit any known classification. The lab lead is left with more questions than answers. Why the delay? Are the instruments malfunctioning? Or is the material itself resisting analysis? Without published data, the scientific process grinds to a halt. The uncertainty spreads, feeding speculation and anxiety among volcanologists who depend on open results to calibrate their models and warn the public. The absence of data becomes its own kind of evidence, a gap that grows more troubling with each passing day. For a volcano as closely watched as Etna, a missing data set is almost as alarming as a sudden spike in seismicity. The lab lead prepares to expand her arsenal of analytical tools, determined to break the silence and confront whatever mystery the mountain has delivered. Inside the lab, the lead scientist stands before a battery of instruments, each one a gatekeeper to the secrets locked inside Etna's latest samples. The first stop is the Electron Probe Microanalyzer, or EPMA. This tool fires a focused electron beam into a polished slice of the glowing rock, coaxing out X-rays that reveal the identity and abundance of elements down to parts per million. EPMA excels at mapping the distribution of major and minor elements, tracing the outlines of each mineral grain, but it can't always spot the finest details or the rarest inclusions. For those, the scanning electron microscope takes over. SEM delivers high-resolution images of textures invisible to the naked eye, exposing the tiniest crystals, glassy pockets, or signs of alteration. Coupled with energy dispersive spectrometry, SEM can pinpoint the chemical makeup of even the most cryptic phases. Next comes X-ray diffraction, or XRD, a method that shines X-rays through powdered fragments of the sample. The resulting diffraction pattern acts like a fingerprint, unique to each mineral structure. XRD is the final word on what crystalline phases are present, even if they're mixed or intergrown. It's the tool that sorts volcanic glass from crystalline feldspar, or detects a new mineral never before reported from Etna. When the standard mineral checklist fails, XRD can still pull a match from the global database, or confirm that the material is truly outside known boundaries. Beyond these core instruments, the lab prepares isotope suites for the mass spectrometer. Isotopic ratios of strontium, neodymium, and lead are sensitive to the source of the magma and any crustal contamination along its path. These measurements require painstaking chemical separation and ultra-clean conditions, but they can trace a sample's heritage back to the mantle or flag, an origin in ancient sedimentary rocks. Each method has its limits. EPMA struggles with light elements and amorphous phases. SEM can be fooled by surface coatings. XRD needs enough material to register a clear signal. Isotopes demand time, skill, and patience. Protocols are strict: clean room preparation, duplicate runs, cross-checks between labs. Every step is logged, every result scrutinized for errors or contamination. The process is designed to leave nothing to chance. In ordinary times, this arsenal is more than enough to identify any rock Etna throws at the world. But with the latest samples, every method faces a puzzle it wasn't built to solve. The lead scientist moves from station to station, searching for a pattern, some thread that will tie these results back to the volcano's long, well-mapped history. Each instrument offers a different angle, a new hypothesis to test. The goal is simple: turn the unknown into something familiar, or admit that Etna has produced a material unlike anything seen before. No two volcanologists in the lab could agree on what exactly had come out of Mount Etna. When the usual mineral checklists failed, the field of possible explanations widened quickly. Some turned to the idea of ultramafic material, rock so rich in magnesium and iron that it usually forms deep in Earth's mantle, not at the surface. If Etna had tapped a pocket of such material, the chemistry would show sky-high magnesium numbers, a near absence of silica, and a texture dense with olivine and pyroxene. But the preliminary scans didn't fit the ultramafic profile. The signature was off. Too many light elements, not enough iron. Others wondered about carbonatite, a rare type of volcanic rock that erupts almost entirely as carbonate minerals. Carbonatite flows have been documented at only a handful of volcanoes worldwide. Places like Oldoño Lengai in Tanzania, where the lava glows white-hot and runs almost like water. If Etna had somehow produced carbonatite, the lab would expect to see a dominance of calcium, sodium, and rare earth elements, with almost no silica or alumina. Again, the data didn't add up. Carbonatite leaves behind a distinct chemical fingerprint, and the ratios in the Etna samples didn't match. A third hypothesis focused on volcanic glass, amorphous material that forms when magma cools so fast that crystals don't have time to grow. Glass can trap exotic elements, sometimes even forming new, short-lived compounds. The glowing material's texture, however, wasn't fully glassy. Scanning electron microscopy revealed a mix of tiny, angular crystals embedded in a matrix that defied easy classification. The energy-dispersive X-ray spectra showed spikes in elements that shouldn't coexist at these temperatures and pressures. Some in the team raised the specter of contamination, maybe something in the sampling process or a reaction between the molten rock and the collection tools had produced an artifact. But the protocols had been airtight, with duplicate samples and cross-lab verification. Every lab returned the same baffling results. With each failed match, the mystery deepened. The lab walls filled with printouts, elemental maps, phase diagrams, and lists of minerals ruled out one by one. Theories multiplied, but hard evidence narrowed the field. What remained was a material that fit nowhere on the established spectrum of volcanic rocks. The only certainty was that Etna had produced something that defied the expectations set by decades of study, a signal that the volcano's inner workings might be shifting in ways no one could yet explain. 40 millimeters every year. That's the rate at which Mount Etna's southeastern flank slides toward the Ionian Sea, a relentless, almost imperceptible movement that never truly stops. The numbers come from a network of seafloor GNSS transponders anchored more than 1,000 meters below the waves, quietly recording the mountain's slow escape. Unlike the dramatic bursts of lava and ash above, this motion is silent and steady, measured in millimeters but carrying the weight of centuries. Onshore, GPS and INSAR satellites confirm the trend. The eastern and southeastern slopes inch outward, sometimes in sudden bursts linked to dike intrusions or seismic swarms, sometimes as a creeping drift that continues even in periods of apparent calm. The real surprise comes offshore. Data from the 2016 to 2018 seafloor deployment showed that the submarine slope is not just following the mountain's lead, it's moving faster, and in some places, almost independently. Displacement rates offshore outpace those on land, suggesting a deep-seated instability that could be decoupled from surface events. High-resolution bathymetric surveys have mapped ancient slide scars and debris fields stretching kilometers across the seafloor, evidence that this creeping motion has, at times, given way to catastrophic collapse. Geodesy teams track these changes with a mix of awe and apprehension. One lead scientist, reviewing the latest displacement vectors, described the mountain as a living mass, always seeking the path of least resistance. It's not just magma pushing upward that threatens Etna's stability. It's gravity, water, and the slow grind of tectonic plates beneath Sicily. Coastal leveling surveys show that this instability doesn't stop at the shoreline. Vertical shifts of several centimeters have been recorded along inhabited stretches, putting towns and infrastructure within reach of the mountain's restless flanks. Every new data set adds to the sense of urgency. The creeping motion is not a relic of the distant past. It's happening now, in real time. The mountain's current behavior echoes patterns seen in the prehistoric record, just before the last great collapse sent a wave of rock into the sea and reshaped the Mediterranean coast. For the scientists monitoring each subtle shift, the question is no longer whether Etna will move, but how quickly, and what might trigger the next major event. Long before written history, Mount Etna unleashed a disaster so vast that its traces still shape the seafloor east of Sicily. Marine geologists have mapped the evidence, a debris avalanche stretching for miles beneath the Ionian Sea, its jagged blocks and fine sediment blanketing the ocean floor. Radiocarbon dates from sediment cores pinpoint the event to about 7,200 years ago. The numbers are staggering. Over 22 cubic kilometers of rock and ash sheared away from the mountain's eastern flank in a single catastrophic collapse. That's enough material to bury Manhattan under hundreds of meters of debris, all swept into the sea within minutes. The collapse left a scar that's still visible today, the Valle del Bove, a gaping amphitheater carved into Etna's eastern side. But the true scale of the disaster only became clear with the advent of high-resolution bathymetry and seismic reflection surveys. These tools revealed a field of hummocky mounds and chaotic blocks, some the size of city blocks, lying more than 1,000 meters below the waves. The avalanche deposit sprawls across the seabed, its leading edge traced more than 30 kilometers from the present shoreline. In places, the thickness of the debris exceeds 100 meters, a testament to the violence of the collapse. Sediment cores pulled from the deep record a sudden influx of volcanic material, sandwiched between older, quieter layers of mud. Radiocarbon dating of shells and plant fragments caught in the deposit has narrowed the timing of the event to a window between 8,400 and 8,200 years before present, with the best estimate at 7,200 years ago. The debris itself tells a story of chaos. Huge boulders mixed with shattered lava, ash, and even fragments of ancient forests swept seaward by the force of the slide. Numerical models based on the updated volume and geometry of the avalanche suggest the collapse generated a tsunami that raced across the Mediterranean. Coastal settlements, places that would later become towns like Giare and Reposto, would have been inundated by waves over 10 meters high with little warning. The scars on the seafloor and the abrupt changes in coastal sediment layers are silent witnesses to a disaster that reshaped both land and sea. For today's scientists, this ancient benchmark is more than a relic. It's a reminder of what Etna is capable of when its slow creep gives way to sudden catastrophe. Tsunami simulation models run the scenario again and again. A sudden collapse of Etna's eastern flank, 22 cubic kilometers of rock and ash plunging into the Ionian Sea, and a wall of water rising in response. The numbers are unambiguous. Waves over 10 meters high, taller than a 3-story building, would strike the Sicilian coast within 10 to 20 minutes. Giare, Riposto, Asiriale, and the port of Catania sit squarely in the projected inundation zone. The models show water racing inland, swallowing roads and rail lines, flooding neighborhoods, and cutting off escape routes before most people can react. Civil protection officials pore over these maps with growing alarm. One senior officer, reviewing the latest hazard footprint, puts it bluntly. We're not talking about hours to evacuate. In many cases, it's less than a quarter of an hour before the first wave arrives. That's not enough time to empty a school, let alone a town. The models reveal a stark mismatch between the speed of the hazard and the reality of emergency planning. Even the best-case evacuation drills, tested after the 2018 seismic swarm, require at least 30 minutes to move people out of the highest-risk zones. In a catastrophic scenario, the sea would be well inland before the first buses could load. Critical infrastructure is mapped in red: hospitals, emergency coordination centers, and the main Catania, Messina Railway all fall within the area modeled for deep inundation. Ports and harbors, lifelines for supplies and rescue, are especially exposed. The simulations show water surging through low-lying industrial districts, overwhelming flood defenses, and isolating entire neighborhoods. For coastal residents, the difference between warning and disaster is measured in minutes, not hours. The urgency is not lost on those tasked with public safety. Civil protection teams push for faster offshore monitoring, real-time tsunami alert systems, and public education campaigns. But the models remain unforgiving. The time from collapse to impact is so short that even a perfect warning system would leave precious little margin. The hazard is not theoretical. It's mapped, quantified, and, in the words of one official, impossible to ignore. Salvatore Greco wakes before sunrise, as he has every day for 40 years. His vineyard sits on a narrow strip of land between the mountain and the sea, close enough to Etna's lower slopes that the ground sometimes trembles beneath his feet. The soil here is dark and rich, a legacy of centuries of eruptions. Grapevines thrive in it, their roots winding through old lava flows and volcanic ash. Greco's family has lived in this shadow for generations, measuring time by the rhythm of harvests and eruptions alike. On the morning after the June eruption, a fine layer of ash coats every leaf and rooftop. Greco stands at the edge of his property, looking up at the plume still rising from the summit. He remembers the stories his grandfather told, of nights when the sky turned red, of rivers of fire that crept down the mountain and stopped just short of the village. Each eruption brings a new test, but this one feels different. The air is thick with the smell of sulfur. The ash is heavier, grittier than usual. Even the older men in town are uneasy. "You learn to live with the volcano," Greco says, brushing ash from his jacket. "But you never trust it. Not really." For people like Greco, daily life is a negotiation with risk. The benefits are obvious: fertile land, a steady stream of tourists, a sense of belonging to a place both beautiful and dangerous. But the costs are real. Ash clogs irrigation lines, ruins crops, and makes roads impassable. Insurance is expensive, and payouts are slow. Every family keeps a go-bag by the door, stocked with water, documents, and a few days' worth of food. Children practice evacuation drills at school, learning the fastest routes to higher ground. In the past, warnings came from the mountain itself. Locals watched for changes in the color of smoke, listened for rumbles that signaled a new vent opening. Today, the first alerts often arrive by text message, triggered by satellites orbiting hundreds of kilometers overhead. The Copernicus program's Sentinel satellites send back images every few hours, tracking the spread of ash clouds and the advance of lava flows in real time. During the June eruption, Copernicus feeds mapped the pyroclastic flow as it raced downslope, giving emergency officials a head start on road closures and evacuations. For the people living on Etna's flanks, these satellites have become an invisible lifeline. Greco's phone buzzes with updates from the Regional Civil Protection Office, warnings about air quality, road closures, and the latest satellite images. He scrolls through a map showing the fresh lava field edging toward the old stone wall at the edge of his vineyard. The wall has stood for a century, but Greco knows it could be gone by morning if the flow shifts. Neighbors trade news and rumors in the village square, debating whether the latest eruption is just another episode or a sign of something more dangerous. Some point to the strange color of the ash, others to the rapid pace of the lava. Everyone watches the summit, waiting for the next sign. The sense of uncertainty is constant, but so is the resolve to endure. Greco tends his vines, sweeps the ash from his roof, and waits. The volcano may set the terms, but life goes on. For those who live in Etna's shadow, each day is a balance between fear and familiarity, vigilance and routine. The mountain is always there, sometimes quiet, sometimes furious, reminding everyone below that their lives are woven into its restless story. 3 scenarios dominate the minds of Etna's risk planners. The first, and by far the most common, is a continuation of the volcano's relentless activity, frequent but moderate eruptions, ash falls, and slow lava flows. In this case, the hazards are disruptive but familiar. Air traffic is grounded, crops suffer, and towns endure cleanup after each event. The monitoring network, satellites, seismic arrays, gas sensors, remains on high alert, but the established protocols hold. Civil protection agencies coordinate with local governments to issue warnings, close roads, and guide evacuations when needed. For this scenario, the checklist is well rehearsed. Maintain real-time data collection, ensure backup power for monitoring stations, and keep evacuation plans updated for every settlement within the hazard zone. The second scenario is more severe, a partial collapse of Etna's eastern or southeastern flank. Here, the risk escalates sharply. Offshore seafloor geodesy has shown that sections of the submerged slope are moving faster than the land above, hinting at deep-seated instability. A partial slide could send millions of cubic meters of rock into the Ionian Sea, generating tsunami waves between 2 and 4 meters high. The warning time shrinks to minutes. Emergency planners must rely on rapid offshore detection, expanding the network of seafloor GNSS transponders and integrating hydroacoustic sensors capable of catching the first signs of a slide. Towns like Riposto and Acireale, ports, and the Catania, Messina rail corridor all fall within the inundation footprint. For these zones, the action list is explicit. Install real-time tsunami alert systems, conduct regular evacuation drills, and pre-position emergency supplies at designated high-ground shelters. Critical infrastructure, hospitals, coordination centers, and transport hubs require reinforced protection and redundant communication links. The third scenario is the worst case, a catastrophic, single-phase collapse matching the scale of the event 7,200 years ago. Numerical models predict tsunami waves over 10 meters high, reaching the Sicilian coast in less than 20 minutes. The volume of displaced material, over 20 cubic kilometers, would devastate low-lying areas, with water racing inland up to 1.5 kilometers in some sectors. The probability is low compared to daily hazards, but the consequences are so severe that no official can ignore the risk. Offshore monitoring gaps become critical failures in this context. Civil protection officials are pushing for a new generation of seabed geodetic arrays, integrated with satellite-based rapid tsunami modeling, to cut detection to warning times to a minimum. Evacuation plans for high-density areas are being rewritten to prioritize vertical escape, moving people to upper floors of reinforced buildings when horizontal evacuation is impossible. Across all scenarios, the checklist is growing more urgent. Upgrade onshore and offshore monitoring, expand public education campaigns, and rehearse evacuation protocols for both partial and catastrophic events. Real-time data integration between local, regional, and national agencies is no longer optional. The lessons from recent eruptions and from the prehistoric collapse are clear. Every year of delay in closing monitoring gaps or improving warning systems increases the risk that Etna's next paroxysm will catch communities unprepared. The mountain's history is a reminder that the improbable can become reality in a matter of minutes. For those tasked with safeguarding the region, the decision matrix is not theoretical. It's a daily exercise in risk, readiness, and the relentless demand for vigilance. Mount Etna has erupted for over 3,500 years, but its 2024 to 2025 activity stands apart. For the first time, field teams and 3 European labs could not match the glowing material from the latest paroxysm to any known volcanic rock. No basalt, no andesite, and no published petrological data to explain it. Flank monitoring now records a steady 40 millimeters of seaward movement each year, echoing instability last seen 7,200 years ago, just before a catastrophic collapse sent 22 cubic kilometers of debris into the sea and triggered Mediterranean tsunamis over 10 meters high. Yet, despite advanced instruments and satellite monitoring, the true nature of Etna's new magma remains unconfirmed. Scientists have documented the changes and escalated hazard warnings, but key results from the most recent samples are still unpublished. As of today, Mount Etna's warning signs are clear, but its deepest secrets remain locked beneath Sicily. The evidence points to a volcano that is still changing and still demanding answers.